So welcome back. Then we are moving on to the next topic, which is document stores, which are a technology of their own. Who has ever heard of MongoDB? Some of you, right? So it was one of the early companies in this business. There's plenty of them, but they became famous, I think, when they raised $1 billion. That was already 10 years ago, and then continued to grow their business. So where are we? Well, it's kind of transitioning with what I've just told you at the end of the Spark lecture. We kind of took care of tables, and I would even say almost data frames, as long as there's not too much nestedness. So we can store data, for example, an HDFS or S3. We can store it as CSV if we want tables, or Parquet if we want a bit of nestedness. We can open them as data frames with Spark, process them in parallel. If we want, we can also use HBase as a layer to have a tabular structure. And then we can use SQL, which is a very natural fit when we want to query tables or data frames that don't have too much nestedness. And what we want to do now is that we'd like to rebuild that stack, but with XML and JSON. And that means with trees, with nestedness, potentially a lot of nestedness, right? So that is the goal right here. So when we have tables or relational schemas, typically, we always have a schema. When you have a relational table in PostgreSQL, or when you have a data frame in Pandas or in Spark, then you have a schema, right? You have no choice. What happens in the SQL and in the XML and JSON world is that the schema becomes optional. You might have data that doesn't have any schema. You might have plenty of JSON files and XML files that are just in a mess, right? You might have values that don't have the same types always and so on. And that actually has an impact on the sort of products that we get the moment we no longer make the schema mandatory, right? And so this is where document stores come into play. There is a real-world reason for sometimes not having a schema, is that this kind of data that we typically query with XML and JSON very often is going to be data that gets accumulated over years and years and years, right? Like the logs of a company, the logs of a website, meteorological data that comes from the sensors and so on. And you accumulate the data into JSON files for years and for decades. The thing is that when you do that, you regularly change the schema of the data. Maybe you suddenly have new data, you added new equipment that has more data or more precise data. And so from a certain day, you suddenly will have an additional key in JSON. Or maybe people will realize that they can change the schema to make it better. Like they realize, okay, that string seems to often be an integer or always be an integer. So let's change the type from a string to an integer and so on. So basically the schemas, they evolve with time. So every couple of years, you might have a different schema. And that means that if you look at the data over 20 years, then there is no unifying schema because the schema actually changed over the years. And so this is why in the real world, you can have these situations in which there is no schema for that kind of reasons. And this is why we want to keep a bit of flexibility in these technologies to still be able to open that kind of data sets, even if there is no schema against which all the objects are valid, right? So that's for the real life justification. Now, when it comes to this, in the early days, people have tried to hit the data with a hammer and fit it into a table, right? It's worth trying, right? Maybe you can still find a way to map the trees into tables, and then you can just go ahead and use SQL. But I want to give you a sense of why it's not so easy. So let's start for the easy cases. Where is it easy to fit some JSON into tables? Well, this case here is easy because it's flat. There's no nestedness in here. The values are atomic values. There is no nested object, no nested array. So you can map that to one row of a table very easily. Every key, every field in your JSON object is a column. and then the atomic values give you the values of the table, right? You can do the same with XML, right? There are simple cases that would be the equivalent of XML. This you can map to a tabular record, right? Then things might become more complex when you have several objects or several XML elements. It still works if the elements or the objects have the same schema. This is the case here, right? The two XML elements can be validated against the same schema, left as an exercise, actually shown on the slides further down. But because they have the same schema, they have the same structure, you can assemble them together as a table with two records. Who sees that, right? That should be intuitive, right? So these are the simple cases where we can actually fit it into a table. That would be the schema, by the way. You could build an XML schema, and you can map that XML schema to a table schema, right? The sort of schema you could have in SQL. That would be the JSON schema equivalent, right? Again, it's all related. But the problems start coming, and I'm repeating myself, but because that's always the same case, it's when you have nestedness and when you have heterogeneity. This is where you start having problems with this approach. Here's with nestedness. What if you want to force that data into tables? And I really mean tables. I don't mean data frames here. I mean tables where we disallow nestedness in the tables. So what if I have nestedness in my JSON objects and I want to force that into flat tables? Well, in some cases, you can do it. Like here, you realize that name is kind of a nested substructure with last and first. So what you can do is you create a second table. You have multiple tables. You create a second table where you store last and first, right? So all of that nestedness in the array, you put it in another table, and then you use numbers to connect it back with a join to the high-level structure that you have here, right? Does that make sense? Right? We just use one additional table for every nested structure that we might have here. So it's not trivial. You can do it on a case-by-case basis, but you can still make it work in some cases. What about heterogeneity? Well, let's assume that that comes from missing values or additional values. You can also hit it with a hammer and fit it into a table if you put nulls everywhere, right? But that means if you have an extra value, you need to add an extra column just for that one value. And that means you need to know it in advance, right? So it constrains things a little bit. So you might be able to make it work, but you see it's not very elegant. And in fact, if you want to do it in the general case, that you have huge quantities of XML and JSON, very nested, very heterogeneous, then you will realize it's very, very tough to do it in a generic fashion, right? And people have tried. In fact, there are papers that try to do it in a generic fashion. But then the table you get when you use these kind of algorithms is completely unreadable by a human, right? You can map it, but a human cannot understand the data just looking at it. It requires a computer program to map it back. So basically, what we are seeing here is that trying to hit objects or XML documents with a hammer to force them to fit in tables is like trying to put a square peg into a round hole. That's basically an impedance mismatch, as we call it in this world. Impedance mismatch is a term, I don't know if I mentioned it, but it's borrowed from music and electronics, right? It's the idea that when you plug a loudspeakers or microphones, and it doesn't have the right properties, then you might actually break it, or it might not work. So this is an impedance mismatch, and we use the same word in databases when you have not the right shapes. Basically, you want to fit trees into tables. There's an impedance mismatch right here. And this is why we have document stores. When people realize that this doesn't work, you cannot force fit trees into tables, then let's design new technologies that allow us to do that, even if the trees are not even valid, even if they don't even fit in data frames. And so document stores typically allow you to store collections of documents, collections of JSON objects, or collections of XML documents. in a way that a collection can easily contain millions or even billions, perhaps even today tens of billions or hundreds of billions of JSON objects and XML documents, and very easily into the terabytes or even petabyte range, right? So these are the common numbers for a document store. There exists two kinds of document stores. I simplify a little bit, right? But they are basically the JSON document stores and the XML document stores, right? So MongoDB is a JSON document store, stores collections of objects. And there are also XML document stores that store collections of XML documents. But they work more or less in the same way, because if you realize that in both cases these are trees, then the technologies are actually very, very similar. Okay. So now, this would be a collection of trees, right? In that case, it's a collection of 3 JSON objects. And the rule of thumb, the way you should imagine it, is that it's not any collection of any objects. Typically, you want a lot of objects, but the objects should not be too large, right? So typically, you can have thousands, millions, billions of objects. The objects should be at most maybe 10, 20 megabytes, right? This is the ballpark. Some systems have the limit. They take a power of 2. They say, okay, 16 megabytes is the limit. And if the object is more than 16 megabytes, then it's not allowed, right? So keep in mind these 16 megabytes. You can put it in perspective with what I said about HBase, when I said that the data you fit in one cell in HBase is roughly 10 megabytes at most, right? So it's the same ballpark, the same size limit in HBase as you have for an object in here, right? So typically small documents, 16 megabytes isn't that big, and a lot of objects. So very tall and very lean. That's the way to imagine it. If you try to have, let's say, a collection of 5 objects that are gigabytes in size, that is absolutely not the right product. Yes? That depends if you have a XML or JSON. It's basically the same thing. But in XML, you will typically say an XML document a lot. In JSON, you would call it an object. I think that even MongoDB might use the term document as well. So it's a little bit interchangeable, object and documents. In the context of a JSON document store, a document is an object. In the context of an XML document store, there's no objects, right? Because it's XML elements. All right? Does that make sense? Okay. Now you might have systems that say a document can also be an array. You could imagine that, and there might also, you know, it's this debate on whether an atomic value can be considered a top-level JSON value, right? And people disagree on that. So most commonly, a document in a JSON document store will be an object, but you could have systems that also allow you to have an array as a document. Okay? Now, the two major differences with relational systems is first, in a document store you can have a lot of nested structures, and in a document store you can have heterogeneity with no schema, and every object looks different than the other objects. What makes document stores similar to relational database systems is that you can also project, you can also select, you can also aggregate, you can also order. But the one thing they will not do so well is joins, right? They will not offer join functionality. Anybody who wants to join collections will have to implement it themselves in Python or C++ or whatever, right? So this is the idea. The validation is optional, but it can be done. MongoDB allows you to validate your data if you want. You can even validate your data after you have put it in the collection, right? You first put the data, and then you see, okay, does it turn out to be valid against that schema? Then you can also add the schema and say, from now on, I want any modifications and any new documents to always remain valid against my schema. It's just an optional feature in that case. These are some of the technologies that we have, the way you identify the XML document stores, you probably figured it out, is those with an X in the name. So base X exists. These are XML document stores. MongoDB, that's JSON. Elasticsearch, MongoDB. Cloudon, CouchDB, these are all JSON. MarkLogic kind of does both. That was one of the first enterprise-ready solutions for document stores back then. They made it to a famous name with, I think, Obamacare, where they use MarkLogic for the first implementation of the system. All right, so there's plenty of them, but we are going to focus on just one, and that's MongoDB today. But you will see if you learn one, then all the others are actually very, very easy to also learn. So we are going to focus on how to query MongoDB. Before we do that, and before letting you go into the break, I would like to reemphasize a difference that I have made several times between two main approaches to storing data. There is the data lake approach, and there is the good old database approach, right? So the data lake approach, that's when you use S3, HDFS with Spark and MapReduce and so on. You drop your data as files on some distributed file system, and then you query it using APIs like Python, Spark, and so on. Pandas would also be this. And then there is the good old database approach, like PostgreSQL, where you import the data into the database first, and then you query it with the system. And how it is stored is hidden. It's the system that figures it out by itself. PostgreSQL has its own way of writing the data to disk. MongoDB is the same. For MongoDB, you need to first import the data into MongoDB and then query it. And the way MongoDB stores it on the disk is hidden from you. It's quite complex, actually, but you don't need to worry about that. It's not going to be just JSON files as you would have in a data lake, right? It's more complex than that. Which brings us to the break, right after which I'll show you very concretely how you can read data, update data, and delete data from MongoDB collection. Right? So I'll see you at 15 past 9 for the continuation.